that looks like this semicircle. You'll see it. It won't be zeroed at the origin anymore, but you'll at least see that feature, and I want you to appreciate and understand what you're really looking at when you do. All right, so this is for there's something called the Randles equivalent circuit. In this case, I wrote here for a supercapacitor, but it doesn't have to be just for a supercapacitor. There's a lot of places where the Randles equivalent circuit works. In this case, it's a little bit more complex system, but I want you to appreciate all of the different features. This is probably the most important slide in the slide deck today. Okay, this equivalent circuit really defines the characteristics that we seek to extract out of an electrochemical test. This could be a fuel cell electrode, it could be a supercap, it could be a solar cell electrode. So I want you to appreciate all of the different parts of this. So what we have is, I mean, in any electrochemical system we will have an electrolyte, a solution of some kind. It doesn't have to be a liquid necessarily, but it's got to be something that allows ion and charges to flow. So there will be a solution resistance at the front end, and then at the electrode we would have a couple of different kinds of entities. Okay, we think of the double layer capacitance as a pretty pure capacitance, so we're just going to write that as a capacitor. Okay, and that C sub D, and a lot of these subscripts you're going to want to remember as we go through these. R sub omega is the solution resistance. And then down here we have this other component. That's the electrochemical component. Right? So that you could also think of the double layer capacitance as more like an electrostatic term. Right? This is the Faradaic impedance is electrochemical. And then what we do on the bottom part of the panel, we are breaking it down, this Faradaic impedance, in a couple of different ways that you'll see both of them. You'll see both of these ways done in the literature. It kind of depends on, I guess, your preference or what the custom in a given field is. But down here on the bottom, you can break this impedance down into a series resistance and a pseudocapacity. So remember that term. We've talked about pseudocapacitance quite a bit. That comes from those fast reactions on the surface. Or you can break it up into, instead of a RC series component, you could break it up into an RZ component, which has a little bit more physical basis to it, where you have a charge transfer resistance, that's R sub CT, and a Warburg impedance. And the Warburg impedance is something that, you know, has its own set of interpretations depending on your electrochemical system. Okay, so this is getting a little bit complicated. I'm going to leave most of the complication to later in the tutorial. Okay, but this is important for you to understand what's going on here. You'll see these kinds of things written in papers and in technical, even in technical briefings from companies and catalog pages and things like that. So another thing that's important, just taking a step back, removing some of that complexity, is the equivalent series resistance. So another way of looking at the whole system is you could take, instead of having the Randles equivalent circuit, you could just take the entire system and say, I'm just going to call it some Z. And the Z I'm going to use is, it has a real and an imaginary component, and the entire real component I'm going to call the equivalent series resistance, and the entire imaginary component I'm going to call the entire capacitive reactance of the system. Okay, so I'm just going to basically say, well, I'm going to extract, mainly what you do is you extract the equivalent series resistance. However, if you want to relate those terms back to what we had on the last slide, you can do it, right? And the way you do it is that the equivalent series resistance is a combination of that solution resistance that we had and the pseudocapacitive resistance. okay? The series resistance in the pseudocapacitive term, divided by our different capacitances that we had, double layer capacitance, pseudocapacitance here, and the B term as well that depends on those, okay? So you can interpret this equivalent series resistance in terms of the Randles circuit as well. So that's what I'm trying to convey here. The imaginary term, again with that overall capacitive reactance is shown here, but usually this is something that is done to really pull out the equivalent series resistance, okay? All right, so if we had a negligible Warburg resistance, that would be a relatively uninteresting system, but it can happen. And by the way it happens is if you make a material and for some reason your electrochemistry didn't go right in the laboratory and you run an electrochemical impedance test and you don't have the pseudocapacitance that you thought you did, right? This is what you would find. It looks a lot like what we had for the parallel RC network, right? Well, that makes sense because that's what it is. It's our parallel RC network only offset by a finite resistance, which is the solution resistance. So instead of starting at 0, it starts at the solution resistance point, okay? I show this because, you know, I think to some extent, if you're working hard at developing Faradaic materials, things that are going to react, then you're going to be trying things that don't work. And when you try things that don't work and you put it into EIS, if you see something like this, you know. You just look at it and you say, I didn't have reaction going on there. I wanted to maybe, but it wasn't there. And so instead of wasting time with more analysis on that, you just say, well, I missed the electrochemistry here. I'm going to go back and make the material again, okay? Or maybe a different material, right? But it's good in that sense for quick screening. And again, you can extract these resistances out quite easily. Now, real systems, though, look a little bit like that, but not quite exactly. Here you have a real system where you would get this semicircle that would be applicable for the very high frequencies. So at the high frequencies, typically with any of these electrochemical systems, anything that's electrochemically active, you're going to see a semicircle feature. Now, it also depends on your frequency range that you chose, right? Sometimes you won't see it. In fact, if you're thinking back to the second chart from today, we didn't really have this semicircular feature. We had more of this wing to the right. And that was because we had a relatively coarse frequency range. But if we zoomed in, we would find this little semicircular feature. Well, what's the difference between the two? The difference is that when you have high frequencies, you're under what's called kinetic control. So the kinetics of the reaction are controlling the rate, they're controlling the reactance, they're controlling the Faradaic response. So the Faradaic response is the one that depends on chemical reactions, okay, at the surface of the material. So you're limited by how fast your surface actually reacts, okay? And you can see that what happens is as you go to very, very high frequencies, once again, your surface cannot react fast enough, and it looks like you don't have any capacitance at the infinite frequency because it's just oscillating back and forth, and I'm the electrochemical. If I'm at the surface and needing to do some electrochemistry, I can't react fast enough to this varying field, so it just looks like 0 to me. Okay? What about the right side, which we haven't talked much about, but we will a little bit more today in this lecture, but then plenty more in the tutorial. On the right side there is something called the mass transfer control regime. So what happens in that regime is your kinetics are plenty fast, but you can't diffuse your reactants to the surface fast enough. And so you get this linear relationship between your imaginary and real components of impedance, or this linear relationship between your inverse capacitance and your resistance. Okay? So what does this look like in a little bit more detail? In this low frequency regime, which by the way looks like the example that I showed, if you remember that example from the paper, right, it looks more like this. In this case, we have this collection of terms. The imaginary part is related to the real part. In fact, there's a slope of 1 between the two. But if I can just take that curve and look at the intercept, I can actually learn about some of these other terms. So at least I know that the intercept value, right? The intercept value is related to my solution impedance, or my solution resistance, my charge transfer resistance, and then my double layer capacitance multiplied by this thing sigma squared. Well, what's that? What do we think sigma squared is related to? It's related to conductivity. I mean, that's what we would assume. And so I will just say here very briefly, sigma is essentially related to a diffusion coefficient. You can think of that as one form of conductivity, right? It's of your species, of your ionic species. It's related to their diffusivity and concentration. So it is very experimentally dependent. It depends on what your concentrations are in the bulk. It depends on what the diffusion coefficient is for those species, which will in turn depend on temperature. We'll talk more about that tomorrow, right? It will depend on those sorts of factors. But you can relate it to, so once we have the charge transfer resistance, we can actually relate our series resistance to the charge transfer resistance with this factor sigma. Again, that's related, it's very experimentally dependent. We can also relate our pseudocapacitance, right? Our pseudocapacitance with CS in that Warburg term. That's related to sigma very, very intimately, right? It really only depends. C sub S only depends on sigma. Omega is something I control in the experiment, right? So that's an example. I think what we've done here is gone through the basics. What I really wanted to do, so I asked myself what I want students to be able to do after I teach a lecture, right? I ask myself that every time. What I want you to be able to do is read an EIS graph, a Nyquist plot. I want you to be able to read it and understand what the different features are. But the best way to read it is to show that you could read it, is to go and do it. And the great thing about this afternoon is that we have a tutorial that's going to let you do that. Okay, you're going to be able to go into a lab, see a real device. In this case, it's a dye-sensitized solar cell, so not a supercapacitor, not a battery, but also not a fuel cell. And take it and look at the data. Kieran is going to actually show you how to do some curve fitting to that, I believe, right? And so we're going to have, a real opportunity to do something. I will tell you, just as we wrap up here, that I'm very much in favor of hands-on experience, right? There's nothing like hands-on experience. And so we tried to work that into the program here, and I hope you enjoy it. Sorry for those of you who are online who can't do it, but some of these things you could probably find some equipment nearby and try it. So with that, I'll stop and take any questions.